Hi guys, and welcome to another video on exam review. So we're going to be looking at one of the most popular questions that comes out in exams as far as Engine 308 is concerned, and this is interpolation. To be precise, the NID interpolation, which we normally call Newton interpolatory division. So 90% of the time you should expect this question in an exam scenario when you're solving numerical methods and exam. So I've extracted this question from one of your past questions, I guess in 2017, and we are going to try to examine the solution to this particular problem. Now, given the following data, approximate f of 0.05, f of 0.7, and f of 0.43 using Newton interpolatory division. So this is the table that we are given. Now, in the B part of the question, they said find dy dx at x equal to 0.26 using 3-point Lagrange interpolation. Now, for the sake of time efficiency, I'm going to focus on just part 1 in this particular video. Then in another video, I'm going to solve this second part, and in that video, I'm going to introduce us to a new kind of interpolation known as Lagrange interpolation, which is a very, in fact, one of the most important interpolation methods in history. Now, we are going to focus on Newton interpolatory division. Now, this method is very easy and it requires you to be very accurate as much as possible. Okay, you just need to memorize 1 or 2 formulas that are very critical and important for finding the solution of this problem. So quickly, let's dive into the solution like this. Now, we are given this particular set of data, and we want to approximate these values. Of course, I hope you know what interpolation means. Interpolation is the ability to find a particular value of a function, okay, when you're giving known values of that function. So you'll be required to find a value of the function in between the known values that are already existent in that function. So that is what we call interpolation, using existing data to find unknown data. So there are several methods to carry or to implement interpolation, and one of the most important 2 methods are the Newton interpolatory division method and the Lagrange interpolation methods. So we're going to focus on the NID. Now, the formula for NID, the general formula is you can obtain a polynomial Pn of x by solving f of x naught, then plus summation k equal to 1, then you now have n, then you have capital letter F of you have x1, sorry, x naught, x1 down to xk, then you now have x minus x naught up to x minus x subscript k minus 1. So this is the polynomial that you'll be required to obtain. Now, don't be intimidated by this polynomial. I know this one might be hard to memorize, but what you just need to know is that you should be able to formulate this polynomial by yourself easily. Now, let me show you how to formulate this polynomial easily, step by step. Whenever you're given this question, first of all, you go to the table that you were given, then you count the number of entries. I have 1, 2, 3, 4. I have 5 entries. Okay, so I have a system with 5 entries. So what am I going to use for n? So I'm going to use 4 as the value of my n for 5 entries. Okay, so why am I using 4 as the value of my n for 5 entries? Because n runs from 0. N starts with 0. So in the case of when n is equal to 4, if we agree that n starts from 0, so we'll interpolate from 0, so 0, 1, 2, 3, 4. So let's count 1, 2, 3, 4, 5. Is that so? So you have it like this. So that is the trend that you're going to follow. Anytime that you're giving a particular table of values, count how many entries that you're giving, and the value of n that you use to formulate this polynomial is going to be the number of entries minus 1, in this case 5 minus 1. Is that okay? So let's break down how this polynomial is going to look like. This polynomial is going to be evaluated as p4 of x. Okay, so p4 of x is going to be f of x naught. Then in the first instance, we'll have something called x minus x naught. Then capital letter F of, you have x naught, then x1. Then we'll go again, plus x minus x naught, x minus x1. Then we'll now have capital letter F of x naught, x1, and x2. Then we'll now increase again, plus x minus x naught, x minus x1, x minus x2. Then we'll now have capital letter F of x naught, x1, x2, x3. Okay, so we're going to stop when we get to what? X4. Is that okay? So the last value or the last term in this polynomial will be plus. We have x minus x naught, x minus x1, x minus x2, and x minus x3. Then you now have f of x naught, x1, x2, x3, and x4. Is that okay? So this is how to generate the polynomial for p4 of x. So you might say you don't understand it, but let me explain it. So the first term of our NID polynomial, so this is my NID interpolation polynomial. The first term is always f of x naught. In other words, f of the first point given. So this is x naught, this x1, this x2, this x3, and this is x4. Is that okay? So that's the polynomial for you. Now, your first term is f of x naught. Then the second term is x minus x naught. X is the value that we are interested in calculating for. Okay, so x is the value that you're interested in calculating for. So the first multiplier here is x minus x naught. Then you now have capital letter F of x naught, x1. Then observe a pattern. Then the second, the third term will have this x minus x naught. Then it will now have x minus x1, and it's now going to have f of x naught, x1, x2. Then when we go to the next term, we'll have x naught, and x1, then x2. Then we'll now go x naught, x1, x2, s3. So you can see that this term here is always lesser than this one by 1. That's why the formula says that we go from x naught to xk, but the difference in terms, that's the x minus x naught, will stop at xk minus 1 for each term. So if here is 5, the last term here will be 4, and if here is 1, the last term here will be 0. That's why in this particular first term, here is 1 and here is 0. That's why we have only 2 here. So in this term, you have 2 and you have 1. So observe the trend, and you now have your x minus x naught, x minus x1, x minus x2. Then this one will run to x3. And x minus x naught, x minus x1, x minus x2, x minus x3. Then this one will run to what? From x naught to x4. So the most important question I believe will be in your mind is, how on earth do we understand what these terms are for, and how do we evaluate these terms? Okay, you don't need to panic at all. In order to evaluate these terms, this is where you now need to form what I call DDT. So forming DDT. DDT means divided differences table. So this is how we are going to form our divided differences table. And from the divided differences table, we'll be able to evaluate what this is, what this is, what this is, and what this is, and so on and so forth. So let's quickly do that. So to form our divided differences table, we're going to have my xn, that's my first column. Okay, then I'll have my x values. Okay, Then I'll have my f of x. Is that okay? Like this. Sorry. F of x. Then I'll now have what I call f of xi comma xj. Okay. Then another one I'll have is f of xi comma xj comma xk. Okay, so I'm going to build this one until I have the same number of representations as I have in this last stem: 1 2 3 4 5. So I'm going to stop this column when I have xi, xj, xk, xl, and xm. Is that okay? So you permit me to stop there. So I'll keep running. I'll have f of xi, xj, xk, xl. Then finally f of xi, xj, xk, xl, xm. Is that okay? So you're going to stop, and remember these are capital letters, so I'm sorry for using small letters. So they are capital letters. Okay, so they are values that we obtain from our divided difference column. So you can call them divided difference values for each of your subsequent iteration processes. So in the first one, I can call this x naught, I can call this x1, then x2, then x3, then x4. So I'm going to advise you that for those of you that are going to be solving this particular question on your exam books, on your exam booklets, when you write your x naught, you need to give one empty line before you write your x1. When you write your x1, give one empty line before you write x2. When you write x2, give one empty line before you write x3, and so on, like that. Okay, so we're going to have series of empty lines in our paper, like that. So we have series of empty lines. So let me just try to see if I can get those empty lines, freestyle them. They're thin, so I'm just trying to see if I can form a booklet, so bear with me. So you understand why I am actually emphasizing on these thin lines like this to give those empty lines. So you see the reason why. All right, so now that we've gotten up to this point, now my x, according to what was given in the table, was we had x running from 0 to 0.8 in steps of 0.2. So we had x naught being 0, and we now had 0.2, we had 0.4, 0.6, and we had 0.8. Is that okay? So this is kind of like the bottom of our table. So now our f of x corresponding to these values, we have 1.000. So I'm just going to fill the value. I have it's copied somewhere, so I have 1.22140. I have 1 point, sorry, the first one, sorry about that, is 1.00000. So 1.22140, you have 1.49182, you have 1.82212, and you now have 2.22554. Okay, so these are your values. Now the big question is, how do I get this particular value, f of xi comma xj. So f of xi comma xj is simply this value here. Okay, you're going to start with the second one. So you start with the second one, this one minus this one divided by this one minus this one. Is that okay? Did you understand what I meant? So you do this minus this divided by this minus this. Is that okay? So I'll repeat. Let's just set up a calculator so that we can get it. So they call this method divided difference, and they call it divided difference for a reason. So on your divided difference method, let me just pull the calculator like this so that we can all have access to it. So this is my calculator. So this is how we are going to do it. Setting up our calculator, we are going to have this value here minus this value here, which is 1.22140 minus 1.00000 divided by then the corresponding x 0.2 minus 0. Is that okay? So when we evaluate it, what do we get? 1.107. So you're going to put that divided difference value here in between both of them here. 1.107. Okay, so that's how you get it, this one. So how do you get the value that will be in between these two? You do the same thing, this one minus this one divided by this one minus this one. So let's repeat the same process. So if I want us to understand that to save us time, we can understand that the intervals between all the points is 0.2. The intervals between any 2 points is 0.2. So the denominator of all these divisions in the first scenario will always be 0.2. But just for the sake of accuracy, I'll have 0.4 minus 0.2 here. That's 0.4 minus 0.2 in this place. Then in the numerator, what we are going to have in the numerator position is 1.49182 minus 1.22140. Okay, so when I evaluate this, I have 1.3521. So you can see I'm putting it in between 1.3521. So it's very important for you to put the values in between the lines. So this is a 3521. Then to get this value, how are you going to do? So you guessed correctly. So you're going to do this minus this divided by this minus this. Okay, so that's what we call divided difference. Okay, divided difference. So on the denominator, we have 0.6 minus 0.4. Okay, that's 0.6 minus 0.4 on the denominator. Then in the numerator, we'll have 1.82212 minus 1.49182. So let's evaluate. We'll have 1.82212 minus 1.49182. Okay, giving me 1.6515. 1.6515. So remember, you have to give lines so that you can be able to put it in between. So that's the importance of giving those one space lines so that you can be able to put the value of your divided difference in between. Okay, and for this last one, we are going to do this minus this, this minus this divided by this minus this. So in the numerator, I'm going to have 2.22554 minus 1.82212, everything divided by 0.8 minus 0.6 rather, and this gives me 2.0171 here. 2.0171. So I've gotten my f of xi comma xj's. So I'm going to repeat the same process, and the answers will also be in between, okay, in between. Now when I'm repeating the same process, if I want to repeat the same process, I'm going to do this minus this. But this time around, if you trace this particular value back to the origin, okay, remember the first time when we were subtracting, the interval was 0.2. Okay, we increased, we subtracted this minus this minus this minus this minus this. So this time around, you're now going to increase the span of your interval. So your interval is just mapped like this. So you have x2 to x naught. So instead of us saying this minus this divided by 0.4 minus 0.2, this time around we'll have this minus this divided by 0.4 minus 0. So we are increasing the size of our interval by 0.2 in each step. Is that okay? So quickly, we're going to have on the denominator, we'll have 0.4 minus 0.2. So remember how I got it. Just try to draw a diagonal line from here to here. You'll see that it actually enters this box, and try to draw a diagonal line from here to here. You see that it enters this box. So these are going to be the denominator values. So 0.4 minus 0.0, not 0.2. So 0.4 minus 0.0. Then in the numerator values, what we have for the numerator is going to be the new values we just got, which is 1.3521 minus 1.107. Okay, so when we divide it, we'll have 0.61275. So 0.61275. Okay, that's the value you get when you do this minus this divided by 0.4 minus 0. So let's try to find what the value will be here. So can you guess what this value will be? If you want to get this one, you have to do this minus this divided by what? So trace this one back diagonally, you get 0.6. So trace this one back diagonally, you get 0.2. So the span on the denominator will be 0.6 to 0.2. Is that okay? Why on the numerator you have this minus this? So let's implement that. So we have 0.6 minus 0.2. Okay, then we have 1.6515 minus 1.3521. Okay, so that gives me 0.7485, like this. Is that okay? So can you see that we are making progress? Then for this 2 now, to get the value here, you do this minus this on the numerator, and if you want to get the corresponding denominator value, as usual, you can trace this one. When you trace this one diagonally, you get this, and when you trace this one diagonally, you get this. So you can see the span with 0.8 and 0.4. So if we implement that, what we are going to get is, on our calculator, we have 2.0171 minus 1.6515 divided by 0.8 minus 0.4, and that gives me 0.914. 0.914. Okay, so we are still going to repeat the same thing. We're going to repeat this and this to get a value here, and this to get a value here. So if you want to get this value, you're going to do this minus this divided by what? So as usual, you should be able to trace this one diagonally. Okay, you trace this one diagonally. When you trace this one diagonally, you're going to enter what? 0. And when you trace this one diagonally, you're going to enter 0.6. Is that okay? So tracing this one diagonally lands us at 0, tracing this one diagonally lands us at 0.6. So that will make me to implement this to get that value. So let me just make this one thin a little. So I have 0.7485, sorry, 0.7485 minus 0.61275, 0.61275 divided by, we have 0.6 minus 0.0. So this gives me 0.22625. So we have 0.22625 here. Then we'll do this minus this, and divided by what? If you trace this one diagonally, you will land at 0.8. And if you trace this point diagonally, where will you land at? You land at 0.2. So the span between 0.8 and 0.2 is just as the span between 0.6 and 0. So we are doing this minus this divided by 0.8 minus 0.2. So 0.8 minus 0.2, and we now have the last value is 0.9 what? 914 minus 0. What? 7485. 7485. So this gives me 0.2758833. 0.2758833. So finally we now left with two values. So we're now going to repeat for these two values. So in doing these two values, you will trace this one diagonally. When you trace it diagonally, you discover that you land at 0.8. And when you trace this one diagonally, you discover that you land at 0. So the span on the denominator will be from 0.8 to 0. Why? We are going to take the difference between this and this. Okay, so let's do that on the calculator. So we have 0.22275833 minus 0.22625 divided by 0.8 minus 0.0. So this gives me 0.061979 approximately. So we have 0.061979 approximately 9, like this. So you keep repeating the divided differences until you get to only one value. So this is your stop. So remember how we did it? We took to this and this divided by this and this, giving me this value. So you do this and this on the numerator, this and this divided by this and this, sorry, it give you this and this divided by this and this, it give you this, then this and this divided by this and this, it give you this. So after getting it, you now do this and this divided by the diagonal traces, tracing this one back and tracing this one back. You all trace it back to this place, to this column. Okay, so this is your trace column. So you trace back to this place and you trace back to this place so that you know what to divide by. So this minus this divided by 0.4 minus 0 gives you this. So this minus this divided by, you have 0.2 here, you have 0.6. When you do, it will give you this. Then this minus this divided by what? 0.8 when you trace this one, and 0.4 when you trace this one, to give you 0.914. So coming to this place, to get this value, this minus this divided by the trace, here 0.6 and here 0, it will give you this value. This minus this divided by 0.8 and 0.2, it will give you this value, and so on. So when you now want to get the last value will usually span between here and here on the denominator. Is that okay? You do this minus this divided by this and you get this particular value here. So this is your stop value. Remember why we said we are stopping at this. You have to span from n equal to 0 to n equal to the number of your what points. So x0, x1, x2, x3, x4. So that's why we replace this one with xi, xj, xk, xl, and xm, representing 5 points maximum. So this f on the last column will always have the same number of abscissas that we are giving to you on your table. Is that okay? So that's how you know where to stop. And remember now that we can now use this table to get the values that we're interested in finding. So let me show you all our values of interest. So our value of interest for this table is nothing other than this one, this one, this one, and this one. So we just need all the f's along, starting from, you don't need this one, f of x, you don't need it. So you're starting from this particular place and you're just going down. So you just need this, you just need this, you just need this, and you just need this. You don't need to do anything with the other ones. So this value here, this 1.107, corresponds to this first one here, f of x naught comma x1. Is that okay? So this value here corresponds to this one over here, f of x naught, x1, and x2. Is that okay? So that's your f of xi, xg, and xk. So this one compares to this one over here, and finally this last one here compares to this last one over here. So you can write this as your f of x naught, x1. You can write this as your f of x naught, x1, x2, your f of x naught, x1, x2, x3, then finally your f of x naught, x1, x2, x3, x4. Is that okay? So having written it like this, the next thing to do is just to plug these values and our polynomial will be ready. So we are almost rounding up for the polynomial. So our Pn of x is given to us as where n is 4. So I can just write P4 of x. We have my f of what? X naught, then plus I have x minus x naught. So instead of me to write f of x naught comma x1, I'm going to replace it with the value that I computed just now, which is going to be 1.107. Is that okay? So 1.107. Okay, then plus, then the next value is x minus x naught, repeating with x minus x1. Okay, then the next value is f of x naught, x1, and x2. That's this value over here. So your 0.61275. Okay, then plus I have x minus x naught, x minus x1, and x minus x2, and the next value is this one over here, which is 0.22625. Then finally I now have plus x minus x naught, x minus x1, x minus x2, x minus x3, and you now have your 0.061979. Is that okay? So this is your polynomial. So if you've gotten to this point, you've already gotten some marks from this particular question. So what is just remaining is to solve for the question. Said we should solve for 0.05, 0.7, and 0.43. So we want to solve for f of 0.05, f of 0.7, and f of 0.43. So f of 0.05 will be equivalent to P4 of 0.05, which just requires us to substitute 0.05 in this particular, anywhere we see x, we change it to 0.05. That okay? So this how it will be. You have your f of x naught, then plus you now have 0.05 minus x naught, and you now have 1.107, and you now have plus 0.05 minus x naught, then 0.05 minus x1 into 0.6125, and you now have plus 0.05 I'm here minus x naught, 0.05 minus x1, 0.05 minus x2, okay, and into 0.22625, and finally plus, we now have in this last place here you have 0.05 minus x naught, 0.05 minus x1, 0.05 minus x2, 0.05 minus x3. Then you now have the last value, which is 0.061979. Is that okay? So if you have it like this, you will be able to what now inject the values of x naught, x1, x2, and x3 from your table. You already have all these values here, okay, from your table, like f of x naught. F of x naught now is actually, this is your x naught, so our f of x naught is 1. So my x1 is 0.2, x2 is 0.4, x3 is 0.6, and x4 is 0.8. So I have all these values, okay, so I just need to plug it into this place. So this is where our calculator will pop up full time. So I'm going to program my calculator, my scientific calculator, like this, and I'll advise you to do the same. So my f of x naught is actually going to be what? The f of x naught, we remember f of x naught is 1.0, right? So I can write our 1, then plus, we have 0.05. So I'm following it gradually. So 1 plus, so something like this. Let me just take the calculator down a little. So 1 plus 0.05 minus x naught. My x naught, as you can see from the table, x naught is 0. Okay, so x naught is 0. So we now have times. So the first bracket is multiplied by 1.107. So I'm going to put plus, open another bracket, you have 0.05 minus x naught, which is 0.05 minus 0, then times, you have 0.05 minus x1. We all know that x1 is 0.2, okay, x1 is 0.2. Then you now have times the value, okay, that we are given, that's my f of x naught, x1, x2, which is 0.6125. Or is it 6125 or 61275? 61275. So 61275. Okay, please take note of errors before you solve. And you now have plus, we'll have 0.05 minus x naught. I'm here now. I'm currently here. 0.05 minus x naught, which is 0, times another 0.05 minus x1, which is 0.2, then times another 0.05 minus x2, which is going to be what? Okay, very good. x2 is 0.4. Okay, that's x2, as you can see, 0.4 here. x2 is 0.4. Then you have, after 0.05 minus 0, 0.2, and 0.4, you have the term from your divided difference table, which is 0.22625. Okay, and you now have your plus, leading us to the last product. You now have 0.05 minus 0, times 0.05 minus 0.2 as for this place over here, and times 0.05 minus 0.4, then times, we'll now do for x3, which we all believe is 0.6 if you have your table. So 0.05 minus 0.6, then everything multiplied by this last value here, which is 0.061979. So we are ready to press equal to and see what we'll get. So on pressing the equal to button, what we now have is that my f of 0.05 is equal to, or is approximately equal to, I have 1.051259. Okay, 015. So let's leave it as 6 decimal places. So 6 decimal places for accuracy. So using the same convention, we can evaluate our f of 0.7 and f of 0.43. Okay, so this time around, since you've already keyed in these values in your calculator, since you've already keyed in this polynomial to your calculator, the only thing that you will need to replace is anywhere you see 0.05. So when we are solving for 0.7, let's just change it to 0.7. So replace all 0.05 with 0.7 like this. Since the polynomial is the same, 0.7. So I hope I'm not going to miss anyone. 0.7. So I have 0.7. All 0.05 will be replaced with 0.7. Okay, 1, 2, 0.7, then 0.7. So it's that straightforward, just your ability to understand. So for 0.7, now that we've done all the replacements, we'll press equal to, and what we have is 2.13770. So 2.0137 and 70 approximately to 6 decimal places. And finally, for 0.43, all you just need to do is to replace every 0.7, 0.43. Okay. So if you have a scientific calculator, to save yourself stress, 0.7 with 0.43, 0.43, 0.43. I hope I'm not going to write 0.34 when I'm trying to write 0.43, because that's like a common mistake. People normally swap numbers. So 0.43. Is that okay? So I hope I replaced every 0.7 correctly. And finally, we have 1.535995, which is 1.5359996. Did you replace it correctly? So let's examine again. 0.43. Oh, I missed 1 point here, 0.43. Okay, so I think that's why it's giving me. So this is what I'm supposed to get: 0.537251. 0.537251, like this. So to 6 decimal places. So this is about NID. So I hope you understood the procedures for evaluating NID. So just to repeat everything from the start, when you're writing, if you want to win the heart of your lecturer, you can actually try to state this formula here. Okay, but the most important thing is understand how to expand it and understand where to start and where to stop. Like I said, if you want to know where to stop, count the number of ordinates that you're giving in your table. Here we're giving 5 ordinates. That means my n is going to be 5 minus 1, which is 4. So why am I choosing n as 4? Because n runs from 0 to 4, and 0 to 4 will still take me back to 5 ordinates. So when you now expand this your p, okay, when you expand your Pn of x, that's taking the order as 4, a 4-point interpolation polynomial, Newton interpolation polynomial. You're going to have this expansion. Remember how it's built. It starts from f of x naught, and it now runs x minus x1. Then the first divided difference. This is the first divided difference. This is the second. Then this is the third, and this is the fourth. Okay, so for a 4-order system, you're going to have 4 divided difference. For a 5-order system, you have 5 divided difference, and so on and so forth. So you see that the bracket in x is increasing gradually from x naught to the subsequent point in the point q, like that. So it increases, the multiplication increases, then we now have our divided difference coming in as well. So this is your divided difference table that you use to get your divided difference. Then once you now get it, you now have to plug those values that you obtain. Remember that the only values you're focusing on is the value along this first diagonal here, starting from this point down to this point. So these are the values you're interested in. You can discard other ones. Then remember, as you're writing your ordinates, you need to give space in between lines, like one line spaces, so because you're putting the divided difference in between the lines too. Is that okay? As you progress. So remember to trace back the diagonal so that you know the span of your denominator. You understand what I mean? Like when we're doing for the difference between this and this, to know the span of the denominator, we had to trace back to get this point, and we traced from here to get this point. So the denominator will span from 0.8 to 0, and to give me what I want. Is that okay? So that is your polynomial. When you now put it like this, all you just need to do is to find all these values. F of x naught can be gotten from the table, x naught can be gotten from the table, x naught, x1, x2, x3 can be gotten from the table. After finding it like we did, then the next thing for you to do is just to substitute the value of x given. So the value of x given will now come in. Like for this case, when we're dealing with this particular value, we had to just replace all these positions with x. Is that okay? So that's why in my calculator, I was just deleting this value and replacing it with the value of x I was asked to find, because every other thing will remain constant. So with this, you can use your NID to approximate the value of your unknown points. So this brings us to the end of this video. You could try solving another question with NID with this particular technique I've explained to you, and hopefully you get the correct answer. So we are going to go to another particular method of interpolating, which is the Lagrange method. So the Lagrange method can be used for interpolation. It can also be used for numerical differentiation. So in the next video, we're going to be examining Lagrange interpolation and numerical differentiation, and we'll subsequently see the easy solution to this particular question using Lagrange, the 3-point Lagrange interpolation. So I hope you've learned something from this video. If you've learned something, give it a thumbs up, like it, and subscribe to my channel. Share, hit the notification bell to stay updated, and all the best in your exams. So bye. Thank you very much.